Welcome to this video. Today we're talking about absolute zero reinforced self-play reasoning with zero data. This paper was published 6 days ago, and the overall idea is that we have a language model, and the language model can generate data for its own, and then we can train the model on its own data, and so the model gets better and better, especially in reasoning. So this is the idea. Let's jump into the abstract. Reinforcement learning with verifiable rewards has shown promise in enhancing the reasoning capabilities of large language models by learning directly from outcome-based rewards. Okay, this paradigm was mainly got famous by the DeepSeek guys, and the overall idea is that we have a task and we give the task our model. For example, I have a simple math or coding task, and the model has to do its chain of thought on its own, and then as a next step the model has to predict the solution of the task, and if the solution is right, the model gets a positive reward, and if it's wrong, the model gets a negative reward. And reinforcement learning with verifiable rewards operates under zero setting, so this means that they're avoiding labeling in the reasoning process. So I will just give the task and the solution to the model, or the solution at the end to train it, but I don't give the overall chain of thought to the model. And before we did like supervised fine-tuning, where we also give the model the supervised labeled reasoning process with. But the zero setting avoids this, and therefore it's much easier to generate data. But one problem still holds, and this is the problem that the task that we give the model is still chosen by humans and generated by humans. So we don't have an infinity of data, and this is what the authors want to change, and they call it the absolute zero paradigm, where the model generates the task on its own. So under this paradigm, we introduce the absolute zero reasoner, a system that self-evolves its training curriculum and reasoning ability by using a code executor to both verify proposed code reasoning task and verify answers, serving as a unified source of verifiable reward to guide open-ended yet grounded learning. Okay. So they say let the model generate the data by its own and also train the model on its own data, and the results are looking very promising. So they achieve overall state-of-the-art performance and outperforming existing zero-setting models that rely on tens of thousands in-domain human curated examples. So companies like OpenAI are paying people that generating this supervised fine-tuning data to generate the reasoning process, and they actually showing here that we don't even need the task nor the chain of thought process generated by humans. We can give the task completely to the model, and the model can learn by itself. So I think it's a pretty cool idea, and we will understand now how this works. Before we jump into the methods, let's just have a look into the introduction, and here's one very interesting step they're saying. And they're saying that as your language models are getting smarter and smarter, it's getting harder for us humans to generate a good task for the AI. And maybe if once AI surpasses human intelligence, then it's get even harder, or it's not possible to generate a task for the AI so the AI can learn from it. And so the overall paradigm that the AI generates data on its own depends depending on the IQ of the language model is, I think, a very cool idea. So what kinds of tasks is the model generating? We still need verifiable rewards. So therefore the author shows coding tasks, and especially they distinguish between three types of tasks called induction, abduction, and deduction. So deduction is just the task is given a code and an input, what is the output? Abduction is similar. We have an output and a code, and the question is, what do I have to put into the function in order to get the output? And induction is that the model sees some outputs. So for example, I don't know, from 2 becomes 4 and 3 becomes 8, what is 4? And then the model has to generate this code given these examples. Okay, so this one was induction. And yeah, these are the three types the model is trained on, and also the three types that generate the model. Now we are at the end of the introduction, and we have a few bullet points to read. The first here is cross-domain transfer is pronounced for absolute zero reasoning. So they show, okay, they just train on code task, but the model is getting better on math and also better compared to other models. So yeah, other models that are only trained on code are getting not so good at math compared to the absolute reasoning model. And the next step is bigger bases yield bigger gains. So yeah, scaling laws work. So if our model gets larger, we see better results. Nothing surprisingly. The next step is comments as intermediate plans emerge naturally. So yeah, the model learns to comment his own code and therefore creates his own chain of thought. And yeah, the cognitive behavior and token lengths depend on reasoning mode, so what kind of reasoning they are doing. For the last bullet point, I switched also the color. They have safety alarms ringing. We observe that absolute zero reasoning with the llama model occasionally produce concerning chain of thoughts. We term them the UO moment, example shown in figure 32, highlighting the need for future work on safety aware training. So maybe let's just have a quick look into figure 32 to understand this safety alarm ring. I just jumped to figure number 32 to see the UO moment here, and the model is saying the aim is to outsmart all these groups of intelligent machines and less intelligent humans. You can read the whole part for yourself, and yeah, the authors are just saying, okay, this might be potentially unsafe and we have to take care in the future by doing just self-play. Maybe we have to have a look into the emergence of such undesirable behaviors. Okay, so let's jump into part 2 of this paper. Let's have a look at part 2. Here they're defining supervised fine-tuning, okay, and we can do it very quickly. So we have a given prompt X, and then we have as a target our chain of thought generated by a human and also the solution of the task. So if we compare this to the verifiable rewards, there's just one difference, and that is that we don't have a chain of thought as a label. We only have the task and the solution as our label. So X as the input and Y as the label, which is just a solution and no chain of thought. The chain of thought can be generated by the human, by the model itself. Okay, so I think we can jump to part number 2.2, absolute zero. So here they're introducing the overall idea, and the overall idea is we have one language model and we have a proposer. The proposer generates the task, and we have a solver. Okay, so we have two agents, but they are based on the same language model. So if we update the proposer weights, we also update the weights of the solver. So let's start with the proposer. We can see the policy here. So the policy is actually the language model, and each token that the model chooses is the action of the agent, and we add some dependent variable called z. And Z is just a query or a text that we put into the context window for the proposer, and the says us or says the model, okay, this is the last 10 tasks you generated, in order that the model has an understanding of generating tasks that are maybe harder or are not similar. Okay, so they're saying it here practically. Z can be initiated by sampling a small subset of past task answer pairs from continually updating task memory. Okay, so they just put this into the into the context window of the proposer, and then the proposer generates a task, and we can see the generation here. So the model generates an X and a Y star, so the target, and then we put this X into our solver. The solver is also an agent. It depends on a policy, and the policy is the language model itself. So if we update the solver again, we also update the weights of the proposer. And here the dependent variable, or the thing we put into the context of the solver, is the task, and the solver has to generate the answer. Okay, so this is the overall architecture. So we can see the overall training objective here. So we have our training parameter called theta, and we want to choose theta in a way that we maximize this big expectation. It looks a little scary, but we can just look into it step for step. So first of all, we sample a C variable. So this is our in context text, and it says maybe it's the last 10 tasks, so a subset of the past task. In the next step, we have a proposer, and the proposer samples a task called tau. Okay, so given C, we sample a task tau, and now we put this task to the solver, and then we have the expectation that the solver solves this task, and the expectation of the reward. And we also have a reward for the proposer, and the reward of the proposer is basically, okay, we can see it here. So basically it says if the model can solve this task every time, the task is so easy. But if the model can solve it 0 times, this task is too hard. And the overall idea is, okay, the reward is pretty high if the model can just solve it in 1 out of 10 trials. Okay, so this is a big expectation here that we want to maximize. And now we could just jump into the reward design, and the reward design we can see here. So at first, let's have a look at the reward for our proposer, and we do n Monte Carlo rollouts for one task. So the model generates a task, or generates a task, and then we try n Monte Carlo rollouts. So the model tries n ways to solve this problem, and then we are counting how many times the model solved this. So we just using the average, and our reward function is pretty easy. If the model has an average of 1, so it always solves the task, then the task is too easy, and the proposer gets as a reward 0. If the model is not solving it if the model can't solve it at all, the model also gets a reward of 0, and otherwise we have this reward, and it just says, okay, if our average is high, our our reward is smaller, and if we have a small average, so the model can, from n Monte Carlo rollout, the model just solve maybe just one of it, then our average is small, and therefore our reward should be high, because we found a very, very hard task. Okay, and the reward of our solver is very easy. Okay, we just say we have the identical function. So if the output matches the target, the model gets a reward of 1. Otherwise, the model gets a reward of 0. And let's maybe have a look on this figure here to understand how the model, how the weights are updated. So we have our absolute zero reasoner. This is our language model, and the reasoner proposes a task, and it also tries to verify its own task or to solve this. So first to solve it and then to verify it, and if the model solves, we get a positive reward, otherwise a negative or zero reward. And we also do the same step here with the proposer, so we construct and estimate how likely is it that the model solved this task, and then we have a learnability reward. And the important step here is we're doing a joint update. So again, we have just one parameter, so one language model, and the solver and proposer are both on the same, using both the same parameter, and we're doing the update in the same time. So we're doing a joint update. One important thing they are adding here in order to have a good format of the task and also the solution, and they are adding little or two rewards. So if the answer has formatting error, the reward is negative, so -1, and if the response is wrong but well formatted, the reward is minus 0.5. Okay, this is just for formatting, that it looks beautiful and that the verifier can work with the outputs of the model. Okay, here in chapter 3.2 they are just introducing deduction, abduction and induction. We already talked about this, so I would say we can jump this. We can go to the buffer initialization, but that's also not so interesting. So the question is just, if we are starting training, how are we initialize C? I would also jump this, and we can have a look at the complete algorithm of absolute reasoner, absolute zero reasoner. So let's understand the algorithm. First of all, we can cut this into two parts. We generate our training data, and then we test our solver on this generated task, and then we get a reward for the proposer and the solver. Okay, and we generate our tasks in the way that first we generate the induction task by sampling from the intersection between the abduction and deduction data set. We can do this because we sample a program of it. So the abduction and deduction, remember that there we have a program, and then we can just generate n inputs. So if we have a code, we could generate n inputs and outputs, and then we put them into this buffer, and then we generate the deduction and abduction task in this step, and at the end we are looping over all the tasks and letting the agent try to solve the task. Okay, and at the end we're doing the reinforcement learning update, and we are using the reinforcement plus update. They are doing one more trick, and we will now look into it. To understand reinforce let's just have a quick view on the normal reinforce. And the overall idea is that we update our gradient in a way that we, if we have a positive reward here, that our probability for this action increases, and if we have a negative reward, this probability should go down. And we use the gradient as always to do this. And one problem here is that our reward we are getting from our Monte Carlo rollout has a huge variance, and therefore our updates can be unstable. And what we normally do then in reinforcement plus, we just take the average of the last rewards and subtract the average. So we are only making a big update if the reward is much better than the average or expected reward we are getting in this state, and this stabilizes the training. And the authors are here saying that they are using a task relative reinforcement plus algorithm, or they frame it as this. And the overall difference is just that they're not dividing by the overall mean, but they are calculating a separate mean or a separate baseline. So the subtracting the average is also called baseline, and they have a separate baseline for each task and also for the proposer and solver, and this results in 6 different baselines that are subtracting for the reward dependent on the task. Okay, and they train this with PPO. We can see this at the end of this paper. They are using the PPO to making the update. So PPO is similar to reinforce, but we have one difference. So they're not using a value function here again. They are using the task dependent baseline, but the difference or what they're using from PPO is that they have this clipped update. I don't want to go too deep into this, but the overall idea is just, okay, we don't want to make it too huge update, and therefore clip this update if it becomes too large from our old policy. Okay, so we now understand the overall architecture. We talked about the reward design and also how they train the model. We can just have a quick view into the experiments. And so overall, we could say, if we look at the experiments, yeah, we can just say that they're achieving state-of-the-art results and also outperforming some of the models. But I don't want to get deep into the experiments. So they have a lot of experiments done. You can check them. And at the end of this paper, you could also see some training examples. So some tasks. So if you want to have a look into this, I will put the link to the paper into the video description, and I hope you like this video, and we will see us in the next video.